Recorded. Fantastic. Fantastic. Well, yeah, thank you for jumping in and turning that on. Just so folks know, hi, I'm CR Fediment. I am the program manager for Energy Insights within Analytics Indiana at Indiana University Bloomington. We're going to be sharing some general updates with you today regarding, sort of the wrap up of phase one of Energy Insights, which is pretty exciting. So we're excited to get to, share the context of our work with you and get to welcome everybody into 2024. Happy New Year. We're happy to see everybody. I would say, Alexander, whenever you are ready to start, take it away. One other note that I'll make very quickly for our other IU presenters, we are going to break things up and take questions in between each presentation, so that way none of you are having to switch so much in between screen sharing. So let us know once you've finished sharing what you're going to share, and we'll take a few minutes to allow some questions after each of our presenters. Alexander, get started whenever you're ready.
Thank you. I just want to make sure that you are seeing the right screen. Are you seeing just the slide or the presenter mode?
It looks like just the slide. It looks like things look correct.
Good. Okay, so my name is Alexander Gumenik. I'm the guy who collects real-world data in this task force. So I've been working with the installation and functionalization and data collection using MVP kit and some also manual log and initial identification of different types of data before they can be analyzed using AI algorithms. About that further step, further speakers will talk after me. So basically, I will give a little bit of a reminder of why this lab was chosen to be monitored as a test bed for typical type of production facility data generation. So Fibers and Additive Manufacturing Enabled Systems Lab is manufacturing engineering facility that is designed for vertical integration of manufacturing of fiber devices. Fiber devices are fibers with active functionalities, not necessarily fibers for optical transmission. Those are fibers that incorporate various active functionality devices, such as microelectronics and optoelectronics, into the cladding of the fiber in arrays that are contacted in parallel and perform some kind of collective function. For instance, are able to perform 5 senses and stimuli of a human in a fiber or fabric form factor, and those are then integrated into applications such as apparel. Okay, so we basically employ an extensive material processing set of tools that basically result in a workflow for fabrication, multi-step workflow for fabrication of those devices. And you can think of it as a technique for large-scale integration of devices into fibers in a similar way that is done with microelectronics. So we control multiple materials, processing them from a molten state in order to create architectures that are meaningful in terms of device functionality, with geometries that we control by techniques such as 3D printing and miniaturized length scale that many times goes beyond the micro scale. We start from fabricating a thick and short preform, which is a scaled up replica of the final device, which cross section has the metals, insulators, and semiconductors in a combination that is designed to impart to the final device its functionality. And then we dip it into the furnace of the draw tower. It softens to a viscous liquid, and then we draw it like a honey strand into something thin and long, which is a fiber. And if we do it right, the cross section of that fiber has the same geometry, just scaled down as the preform. And then we also have a set of techniques where we can chop in the axial dimension initially continuous cores into discrete devices, such as p-n junctions contacted in parallel by metallic buses to form, for instance, one-dimensional imaging array. So it's a lot of that, just to say that we have a lot of equipments that are large power consuming equipments, high temperature power consuming equipments, including this is a cross section of my lab. So it's 2 stories lab with which is fully packed with a order of 60 machines. It includes optical labs with electronic characterization equipment, but also a lot of fabrication equipment. Like here you can see CNC machine and the lower level of the draw tower, and we have a bunch of 3D printers, both for polymers and glasses, and we have hot presses that go. We have a hot press that goes up to 25-ton load, 2,500 degrees Celsius, so it's high power, and glass lace, so that's also a high thermal output, but not necessarily high electrical consumption, although it has an extensive automated control draw tower. So a typical process that is shown here, which is the fiber draw, is fairly power consuming. So
Alexander, sorry, we just see your face. We don't see the presentation.
Is it only Hamid that doesn't see the presentation? Or no one sees
I can
the
see it.
presentation?
I
can
can
see
see
it,
the
no problem.
presentation.
Yeah, I think most of the rest of us are able to see it.
Yes.
Hamid, if you have any problem, write it in chat so it's not disruptive to others. Okay. So you can kind of imagine how power consuming this is, because in order to melt the glass to the state of viscous liquid, you have to heat it up to 2,500 degrees, where everything glows like a Christmas tree. And in order to run that furnace, we employ a 3-phase power with a dedicated transformer that is capable of generating up to 50 kilowatts of electrical energy. So then, after you melt the glass, you need to start applying a set of mechanical equipment that draws the fiber, and in addition, you have coating that is then cured by high power UV lamps. So UV lamp for curing the coating is consuming a lot of power. So you basically have a complex workflow, even in just this one step, and depending on how far in the workflow you go, there is a hierarchical set of events that are developing. Okay, and depending on the specific process that you are doing, you will have different power consumption, not just in the furnace itself, but also in all the subsystems that are kicking in, sometimes by user and sometimes automatically, and will also have power consumption. So arrangement of control over this hierarchical development of events is one of the questions that will help optimizing the power consumption. So just to summarize, it's a real world small scale factory, okay, that has all the steps for fabrication of devices. And if you map all the machines, you have order of 50 to 60 machines that are working operational, and you use a different combination of them to create different types of devices. So you might start from a 3D printer to 3D print a preform. It has its power consumption. Then you sinter that preform with a hot press, for instance. It has its own power consumption. You can post-process it mechanically with CNC. You can then encapsulate it in a larger tube in order to be able to feed into the draw tower with a glass lace, and then you draw the fiber, and then you post-process the fiber, and then you can characterize the fiber or integrate it into specific application. Okay, so there is a number of steps, order of 10 steps for fabricating each device, arranged depending on the design of the device, hierarchically evolving on the level of the factory flow and on the level of specific machine. So we have that lab it's factually a building inside the building, so it's easy to monitor the power consumption of that. And in the way we have installed the MVP kit, we have been able to monitor maybe not the whole lab, but a large set of subsystems of that lab. So in order to monitor the whole lab, if I'm not mistaken, we had to have seven detectors, and we had only 3. So we are monitoring incomplete subset of what's going on in the lab, but it also already has a large number of equipments monitored by just 3 detectors. So usually when you get to see what is the output on the dashboard, you have a very complex signature, different aspects of which are not so easy to attribute to operation of a specific machine. The only exceptional case that is drawn here with the red enclosure is the high power, high temperature furnace of the draw tower that is connected exclusively to one single detector. So you have just one clean type of signal, and all the others are usually mixed, and you have to employ almost like detective techniques in order to figure out what is what, which power consumption is attributed to each device. So to show you how signal recognition is done when it's done manually, we have a dashboard. Obviously, the first example that I'm bringing is identification of a signal of the high temperature draw tower furnace, because this is straightforward. You have normally a signal that is 0 until you kick in the furnace, and then you start seeing power consumption. It's easy to recognize, okay? But if you look at other devices while operating this draw tower, you can see that there are all kinds of subsystems, including gas, cooling, control cabinet, mechanical subsystems that kick in earlier. So this is the signal. Those 2 big sets of 3-phase power consumption is the draw tower, but around them you have a signal on the second detector and on the first detector that are showing how other subsystems are kicked in before the draw tower is operated and kick out after. They taper out after the draw tower is turned off. So, for instance, if you have a cooling system that is supposed to automatically cool the furnace after operation is done, it is managing itself. So it's not user managed. It's a PID loop that measures when the shield of the furnace is cooled down to the right temperature that is safe to the user and to the equipment. So that taper out time might change from process to process. Shorter processes will have a shorter cool down phase. So it might, and that dependence, we didn't investigate it enough, but that dependence might be nonlinear. So roughly speaking, if you can accomplish the same device fabrication in 2 processes that are twice shorter than are needed in order to overall fabricate this device in such a way that the taper out is faster for each one of them compared to their sum, right? Then you would create a different scheduling because that would be more optimal for the power consumption. And that's one of the things that we need to investigate. So there is a complex dependence here. Some of the processes are user triggered. Some of the sub-processes are user triggered depending on when the first process was triggered. And some processes are automatically triggered and automatically tapered out without any control of the user, depending on the processes that the user controls. So then we have a low power furnace, which is connected to a different detector to which another order of 10 pieces of equipment are connected. So we had to relate a specific shape of signal in the detector that we measure to a log file of the draw tower itself to kind of visually identify that there is a resemblance between the log of the computer of the draw tower and log of the kit on one of the phases of one of the detectors. And then we were able to say, yes, we know how to, by detecting the shape, identify what is the operation of the low power, low temperature polymeric processing furnace of the draw tower. We also have been from some point on logging all the big equipments, and then have been investigating which equipment has been operated at which time in order to identify the signals that are associated with operation of this equipment. So for instance, this is a 3D printer, production grade 3D printer, Fortus 450 MC made by Stratasys. And we can see that we know that it's connected to 3 phases. So this is power consumption of Fortus, while on the same detector, you can see kind of similar shape, but it's only on 1 phase, okay? And we have to identify a signal from the printer. We have to monitor all 3 phases of a particular detector and see signal in all 3 phases. Then we know that is related to Fortus. Why if we see signal only in 1 phase, that's something else, which we don't really know. So it's kind of investigation every time to detect. One interesting example is the rheometer. Rheometer is the measurement system that measures viscosity of materials. It has a piston that is controlled by pneumatic input. Okay, that is connected to a compressor. So we kind of identified the signal of the compressor by its shape. It's not a PID control, it's on and off control that has periodic behavior. So the chamber of the compressor slowly leaks. At one point, it turns on fully in order to compensate the pressure, and then turns off. And you basically have a periodic tooth function that is maintaining the chamber of the compressor at a constant pressure at all times. We paid attention to the fact that sometimes the frequency of operation of the compressor increases. And we wanted to understand what is this related to, and we finally, after some investigation, found that on the signal that monitors inlets in this room, there is also a small rise here that is correlated with the consumption of compressed air from the compressor. Okay, and then knowing in which room the equipment is, we have been monitoring the use of equipment only in this room, and then we identify that it's related to rheometer. So it's almost like an investigation every time you want to understand the signal. And then basically, we found that we can identify signals related to order of 20 different machines, okay, and out of 60. And those are the machines that we are logging in every time they are used, such that we can attribute a use of each machine to a signal in the dashboard. But there are signals that we have no idea where to attribute them, because we don't control the triggering and we don't control its tapering out. So for instance, we see a signal that has weekly periodicity, okay? And that it turns on every day, it turns out every end of day, and turns on 5 times a week from Monday to Friday. That has to be somehow related to air handling. That's what we think. That's the best candidate, but we are not sure, because it's controlled by automatic loop that user has no interference with. Another thing is a signal that we see every Wednesday from 6 a.m. to 6:30 a.m. on one particular detector every week. exactly starting at 6 and exactly ending at 6:30. That must be some kind of software update, regular software update. It's too periodic and too repeatable. But we don't know what it is. So we loosely attribute this signal. That's pretty much our progress so far. Analysis of that is, I hope other guys will talk about. Any questions?
No one has any questions right at the moment, then I think we'll probably jump into our next section just to make sure we're keeping things moving along timely here. Alexander, thank you so much for that first section. We certainly appreciate it. And Ariful, whenever you're ready to take it away, we are happy to have you start your presentation. As Ariful is finishing getting that set up and coming off of mute, just so everyone knows, if you have any other questions that you'd like to add, feel free to drop those in the chat. We'll make sure we get to them in between presenters. Ariful, go for it.
Okay. Can you hear me and see my screen clearly?
Yes.
Yes.
Okay. I'm going ahead. So thanks, Alexander, for discussing his beautiful lab and how we collected data. So now we'll be discussing about some data analysis, how we analyze those type of data and our recent results. So as Alexander mentioned, like his lab is like a model for of how a manufacturing process will operate. So we think about this process as an interoperability of three things: and manufacturing process where worker will perform some jobs with some machine, and that will generate some data. And then we store data and, for example, energy usage and other features. And those data can be analyzed to make some decision like scheduling or something like that. So in order to move toward a digital twin of manufacturing, we consider that those whole process, like process, data, and analysis, they can be done inside a computer using automated models so that we can make some automated decisions. So we read many papers on this topic. Here is this brief set of papers that are published in recent years discussing about how to capture manufacturing process using machine learning models or artificial intelligence. So we are following the trend in the literature and trying to develop machine learning model that can understand manufacturing process, analyze the data, and help us to make some predictions. In particular, in this talk, I'll be mostly focusing on this middle part where we have collected the data from a manufacturing process, and we'd like to analyze the data, model the data, and predict the data, what will happen in the future. So in this process, we are also taking into account about the manufacturing process into it, but we are not actively using this in our analysis. But in future, analysis process will be able to also capture the manufacturing process directly inside our data analysis model. So when you talk about a simpler model, so I am narrowing down the scope of this talk, saying that we want to forecast energy consumption in an industrial setting. And the main question that we are trying to answer would be how to predict future values from past data. So this is like a pure forecasting problem. And in our model, we have three components. One is data representation. How can we represent data collected from a complex industrial process? So in our setting, we have a couple of issues, like we have data collected from multiple devices. We can have multiple variables collected from the same device, and each variable is a time series. That means it is varying across time. So that is the data aspect of it. And then we think about the machine learning aspect of it, how to learn from it. So we considered various models. Some of them are based on state-of-the-art like transformers. We also tried variants of recurrent neural network models. And finally, when you learn from those data using a machine learning model, we get some prediction. Can we interpret the result? That is very important for practical uses. So we also try to understand that, like how our model is predicting from input variables. So those are the three components that are part of our forecasting model. And we are doing this with 3 data sets, one from EMC2, another from our industry partner Amatrol, and the third data that we collected from Alexander's FAMES lab. So when you represent the data, the first component of our model is data representation. So since this type of data, we collect data from multiple devices, each device will have multiple variables. And different devices, they are connected through a hierarchy. So we try to capture those relationships using a graph, where each node or each circle here, they represent a device or a variable or something like that. So for example, in our original data set from EMC2, we had 5 layers. In layer 4, that layer, in that data, layer 4 capture different devices like air handling unit, hot water system, and so on. And the 5th layer in the data actually capture the actual time series like air temperature, supply fan speed, air humidity, and so on. So we can capture all of those aspects of data using a graph like this. It may seem complex, but the actual data, actual time series are captured at the leaves of this tree. So those are these green dots that represent the actual time series data that are captured from these devices. Similarly, for our industry partner Amatrol, they have similar data set, and we can see clear hierarchy there. For example, they have different HVAC units, power meter, CNC machines, and they have other components. And at the end, in the leaves of this tree, we see actual variables, actual time series that are captured from different devices. So this is how we decided to represent our data. It can help us to understand the data as well as how to analyze them, because data items are related in certain way, and we can capture that in our machine learning model. So after we capture the data as a graph, then we think about how to predict from this type of data. So initially we consider several settings. One setting is called univariate model. In univariate model, we predict future values of a variable based on the past value of the same variable. That means we don't consider any other variable from other devices. And there are many popular machine learning methods that can be used in this regard, such as recurrent neural networks, LSTM, GRU. They are very popular and standard machine learning models for those type of cases. But as I mentioned, in this data, we have multiple variables coming in from multiple devices. So we consider multivariate setting where we want to predict one variable, let's say energy usage or power consumption, based on many other variables such as temperature or humidity and other stuff. That can be done through a multivariate model. And the key question there is, do all variables need to be considered for a target variable? So it is possible that for the target variable, not all variables are important. So we have to identify what variables are important, what variables can be used to improve the prediction. So we consider those aspects as well. And we also consider multi-device setting where we have multiple devices. Maybe one company may have 5 HVAC units. Do we want to use all 5 HVAC units to predict something? Is it useful or not? Can we automate this process and so on? So we try to capture all those aspects in our machine learning model. So here is a very high level diagram of the model that we are using at this moment. So the main component of this model is a recurrent neural network, but we try to apply 2 levels of attention. One is called temporal attention, another is called spatial attention. So spatial attention is like if I put 100 variables from 10 devices into this model, it will try to select some of those variables that are important for prediction. And that can be done through attention mechanism. We call this spatial attention. This is nothing but a weight to incoming variables. If the weight is set to 0, we simply ignore that variable. If the weight is greater than 0, that means we are putting some importance to that particular input variable. At the same time, we have temporal attention, meaning that if we want to predict what will happen next hour based on the first 100 hours or so, then it is possible that some of those time steps are important in the prediction. So we can use temporal attention to identify important events in the past so that we can use that to improve the prediction. So the key features of this model is it has both spatial and temporal components, meaning that it can try to select variables, it can try to select time steps that are helpful for a prediction. It can also capture multiple variables and multiple devices across in our data. And the attention or the weights that we are discussing, they are learnable, meaning that if we want to move the model into a different setting, it will learn how to interpret those data, and it will learn those attentions so that we can customize the model, or we can transfer the model from one setting to another setting without any problem. So when we train the model, we pre-process the data a little bit, and then we used 70% data for training, 20% for validation, and 10% for testing. It can change across different settings. We tried 3 different data sets, as you mentioned, from EMC2, Amatrol, and FAMES lab data sets. So those are the 3 data sets that we used. So we did a lot of experiments with a lot of models. So ARNN is the model that I discussed, but we also tried many other models published in the literature. Some of them are transformers, like FATformer is one of the recent transformer model that is that performs really well for predictions. We tried some very recent papers published last year, LTSF, SINET, and others. They are state-of-the-art models for time series predictions. We consider 4 settings as we discussed: univariate unidevice, just one variable from a device; multivariate unidevice, meaning that multiple variables but from the same device; univariate multi-device, meaning just one variable from all the devices that we have. And the most complex one is called multivariate multi-device, where we throw everything from all the device, all the variables together. So those are the 4 settings. And we try to minimize error, meaning that how far we are from ground truth values. And that is measured by root mean square error, where lower is better. And in this table, we mark the best one as bold, and the second best one with underlines. So this table is complex, but just one summary that I want to mention is you'll see that all bold numbers are in this group. And that means for this data, for EMC2, when we try to use all devices, but just one variable, suppose we are predicting energy or temperature or something like that, it is better to use the same variable from all the devices to predict that variable in one device. And that is the best setting for this data. We have not manually tuned it. This model will automatically identify this setting, that this is the best setting for this data. And this is better than just trying one variable from one device. This is the second set of results from Amatrol. And we also tried 4 settings, univariate, multivariate settings. And we tried all those models, some simple models, some fancy models from recent literature. And again, we see that in most cases, using many variables, like in this group, for example, when you predicted true power, then the best model is TCN using univariate multi-device setting. When you are trying to predict apparent power, then the best one was multivariate multi-device setting with ARNN. So summary here for this data is univariate or multi-device settings tend to give the best result for this type of data. And this is the last set of results from FAMES lab, the lab that Alexander described a few minutes ago. And again, here we see that the best results are coming from this group, where we consider multiple devices simultaneously. And for different predictions, like when we predict one variable, the best result is coming from one model, but for another variable, it can come from a different model. And this is the benefit of trying many models on many different settings, so that we can identify what is best for a particular data, so that we can identify the best model in the best scenario. So to summarize all those tables, all those results is when you try to predict something in a complex industrial setting, an integrated analysis with all devices and all features may improve the prediction accuracy. And it is hard to do this manually, so that is why we need an automated machine learning model where we can throw in everything and it will identify important variables and give us accurate predictions. Here are some time series plots that we captured from those tables. Here, black represent the ground truth values, green one represent the model that I discussed with attention, and the red one represent the vanilla RNN models. And we can see that in many cases, attention's mechanism can help improve the prediction quality. Here is another example, and we can see that in some cases, the green one, the model that I described, is better than the red one, where we don't use any attention mechanism. But we're still not 100% accurate. As you can see, there's a gap between blue, green, and black lines. So I'll finish the talk with some insights, like why having those attentions is good. And if we have, let's say, 100 variables, how can we select those variables that are important for prediction? So those attention mechanisms that we discussed, they actually help. Here is an example in this particular case. When we predict mixed air temperature, we tried 7 input variables in this case, but we see that most of those variables, they are not used at all, meaning that their attention scores are 0, and the model will simply ignore them. And this is learned through training. So this model identified that 5 out of 7 variables, they are not useful. They don't help improve prediction. It will just improve that. Instead, it will just consider 2 variables, mixed air temperature and preheat coil temperature in this case, that they are actually helping the prediction, and it will pick those variables and assign some attention scores to them. And using those 2 variables only, we can get the best possible performance for this particular prediction. And we can also see that across time, their attention scores also change. And that can also help us to predict future values. If we change our prediction horizon, like if we want to predict next hour or maybe next 10 hours or something like that. So this relationship, like which variables are important, can be very complex. Here is an example from Amatrol, where we can see that when we are predicting true power, many other variables are impacting. Of course, true power is the most influential factor. Past values of true power will definitely impact the future value of true power. And that is what we are observing in this row. But other variables are also helping to predict what will be the value of true power. Because whatever devices we're running, they are using some power, and they should contribute the power consumption. So an attention-based mechanism can actually help us to identify all those variables and their relative importance. In another extreme case where we don't need any other variable to predict the target variable. So when we try to predict humidity, we observe that no other variables are helping. So in this case, the model will simply pick one variable, and which is translated into a multivariate setting to a univariate setting, and this will give us the best possible results for this particular setting. So to summarize, we tried many machine learning models to predict energy usage and other variables in industrial settings. We tried to develop a model that can identify important variables for the prediction. It will give us reasonably accurate prediction. And based on these findings, we are writing a paper on this topic. We did a comprehensive literature survey, so we have a reasonable understanding about the literature. So we will write a paper using all these 3 data sets and all this model that we discussed with necessary interpretation and others. So that is my last slide. Thank you so much. Any question?
I think if that's the case, if we don't have any questions right at the moment, I think we'll keep our presentation rolling right along this afternoon. We'll be coming up to the final section of our presentation that will be presented by Abdul Rahman. So whenever, Abdul, you're ready to get your screen shared or however you want to present, I think we're pretty much ready for you to get started whenever you feel.
Perfect. Can everybody hear me?
Yes.
Perfect. Just give me. Is the presentation visible? Yeah, perfect.
Yes, we can see everything. We can hear you. You are good to go whenever you're ready to start.
Perfect. Hi, everyone. I'm Abdul. I'm a second-year PhD student at IU Bloomington, working with Pratik Sharma. So today I'm going to talk about design and implementation of an extensible data analytics system that we have developed for energy insights in a box. Let's start with the design goals. We had the design goals to provide a low-cost solution to data analytics using on-prem infrastructure that is composed of low-cost, low-power devices, which can actually provide real-time data analytics using deep learning models in real time. The idea was to pull data from sensors into the time series database, provide continuous analytics. I will talk about this loop in greater detail in the next slide. And finally, provide an easy way to visualize the real-time data and the predictions. With these goals in mind, let's look at the implementation that we have. So there are two distinct layers to the implementation, the data storage and the continuous data analytics. The main purpose of the data storage is to reliably fetch the data from sensors and store into a time series database. And the primary purpose of analytic layer is to provide a closed loop to fetch a sensor data, make some analysis, and push back the analysis back into the influx database. So let's start with the data storage layer, which is primarily built using MQTT protocol and influx DB. The data is sourced from up to 22 devices in FAMES lab via MQTT protocol and pushed to the influx DB using a service. So the service connects to the broker and to the influx DB, fetches the data and pushes to the DB in real time. For the analytics layer is developed using an in-house developed analytics framework and TOSERV. This layer is hosted on Jetson Orin, which is a low-cost, low-power device. Each analysis/prediction loop in this layer starts with fetching the data from the DB, making an inference request to a model hosted on the TOSERV, and pushing the data back to the influx DB, where we can visualize the real-time data and predictions on the dashboard. Now I'm going to give a demo of this dashboard showcasing real-time values and predictions. Yep. So here you have a visual of the dashboard. So for the demo purposes, this dashboard has few sensors, but in the background, a lot of sensors, all the sensors are being streamed into the database in real time, and the predictions are being made for 54 set of sensors. So let's take an example as this last sensor, which is a power meter HVAC rooftop unit and power, which is giving a value for power factor. So it shows three set of lines. This orange line is the real-time value, actual value from the sensor. The purple line is the predictions using the ARN model that Ariful was talking about. And ARIMA is just a regular ARIMA regression model using exponential regression. So you can see that if I zoom in, I guess, yeah, these lines are extending beyond the orange line, showcasing that these are the future predictions and they are being updated in real time, as you can see. So So let's talk about what a user can do to set up a prediction for a new sensor in the system. In summary, only 2 steps are required. You just have to write an extensible JSON configuration and run a bash script. The configuration is the key to setting everything up. You have to specify the sensor you want to fetch data for and predict for. You specify the model you want to use. You specify the data analyzer, which depends on the endpoint for inference. If you want TORSERV, it will be a different analyzer. If you want to use a local model, it will be a different analyzer. Then the InfluxDB bucket from which you want to fetch the data. The window size, which is the time frame on which the analysis is done, and the time step, which is the time by which to slide the window for next analysis. And this system also provides different types of processors, historic or real time. Historic processor will do the analysis on a historic data from start to end, and the real time processor will do the analysis, run the loop for real time data streaming into the database and pushing the results to the database in real time. So our implementation is in 5,000 lines of code, broadly encompassing MQTT service, analytics service, and the TORSERV. And we will open source the code soon, but if anyone wants to use the code, please reach out and we would be happy to share. Now let us look at some performance numbers of the system. With the current setup of 54 sensors being predicted using ARIMA model and ARN model in real time on Jetson device, the network bandwidth consumed on the box is approximately 800 kilobytes per second, with 25% of CPU being busy and only 40% of GPU utilization. The InfluxDB storage is increasing by 7 kilobytes per second, which means it would take almost 2.3 years to fill up 500 GB of space. As for our future work, we plan to extend the system to predict 1,000 matrices at the same time, which can be done by distributing analysis across different edge devices or packing more requests on the same box by throttling the requests. We will be improving the query interface to use conversational AI so that it's easy to visualize data. And optimizing the inference requests, scheduling to reduce the cost per inference. Yeah, thank you for listening, and I will be happy to answer any questions.
I'll say it is right about 2:06 in the afternoon. So if anyone, last call, any questions for any of our presenters here today? And if not, I think this is a great place to call it. A huge thank you to Alexander, to Ariful, and to Abdul for your presentations today. We super appreciate you. And to everyone that was able to make it out, thank you so much for your time and sharing part of the afternoon with us. We hope everything was engaging and exciting. And of course, if you have any questions, curiosities, if you're interested in any of the code, obviously, as Abdul was talking about here at the end, please don't hesitate to reach out to me or to any of our presenters today. We'd love to connect with y'all. But otherwise, we'll leave it there for the afternoon. Thanks, everyone.